Hey guys, welcome back to Quick Code. Today we're doing another Brainstellar problem. This one is called light bulbs in a circle. It's a medium problem. You guys can pause and go over the problem once. So imagine a game where there are n bulbs in a circle and all of them are initially on. And now we move around the circle, examining the bulbs one at a time and toggle the next bulb state based on whether the current bulb is on. So how this works is, so let's say our time is equal to t is equal to 0. We check this bulb. Since all of them were initially on, this is going to be on. So we are going to toggle this bulb, the next bulb. So since this was on, this will now be off. On. Currently all of these are on, right? So ticks denote on. So now at t is equal to 1, we check this bulb. This is on. At t is equal to 2, I check this bulb. Since it's on, I toggle this one off. I check this one, don't do anything. I check this one, I toggle this one off. And this process keeps on continuing. It goes on in infinite loop, right? And the goal or the question is basically we have to prove that if we keep on continuing this process around and around the ring, it is always guaranteed that we eventually will end up at the initial state of all of the bulbs again being on. So to give you guys a few hints about this problem, first of all, think about what defines a state over here. So in this system, how I define a state is the current setting of each bulb. So there's n bulbs and each of those n bulbs can either be on or off. And there's also a pointer, right? Where, or basically the time t, wherever we're situated at, which the pointer denotes the bulb that we are about to examine. So, and for that pointer, let's say t, there are n different possible arrangements. Right? So over here, this n means n bulbs, and this is one pointer. And using all of this information, I am defining a state. So a state would look like something like this. Let's say I have bulbs 1, bulb 2, all the way up to bulb n. Now each one of them could either be on or off. So they have 2 to the power n different possible states. And also there's a value of t, the pointer, which could either be, well, since we actually care about t modulo n, this value could be from 0 all the way up to n minus 1. So in total, multiplying all these different possible values, each state is defined by all these possible values, and so there are 2 to the power n into n different states that you could be in at any given point, right? Where any one state is defined by the setting of each of those n bulbs and the pointer t. There are 2 to the power n into n different possible states. Now, the hint is that to have to understand that there are only a finite number of states in total within this given system, right? And try to think about why having only a finite number of states will lead us to a probable way of solving or proving why we will eventually come back to the same state. The second hint is that if you think about it, since there's always the states are always going to progress from state 1 to state 2 to state 3, right? Since it goes on forever, and there's a finite number of states, will the system keep on producing new states, or will it eventually come back to a state that it has already seen before? Try to think about this question, right? Think about this question over here, that once it repeats a state, but first of all, you have to answer this question, because if it doesn't ever repeat a state, that means it's just gonna keep on producing new states. But if this is not true, then that means this is true, that it's gonna repeat a state. And if it is gonna repeat a state, try to think about the question of, once it repeats one state, does it just fall into a loop or not? By loop, I mean a loop of states. So state I to state j to state k, and then all the way back to state I, and then that loops around itself. And the third hint I'd like for you guys to think about is that the way the rules of the system are defined, as you check the bulb at pointer t, and based on that value, you toggle the bulb at pointer t plus 1 modulo n. These rules are very deterministic. So that means that each state has a unique pre-state and a unique post-state. So from one state, looking at that state, looking at the value of these n bulbs and the value of the pointer t, we can deterministically define a unique state which is going to come after this current state. And we can also deduce a unique state from which this current state must have came from, right? So the rules of the system are such that there is no ambiguity. If we look at the current state, we can deduce a unique definite pre and post state. So to summarize the hints once again, we know that there are a total possible states of 2 to the power n into n. These are the number of total different possible states. And the important point is that this number is finite given a situation or given a system, given a value of n. Second hint is that since there are a finite number of states and the system keeps on going on forever, if you just think about it, it is guaranteed that the system is eventually going to reach into a state that it has already seen before. So that means loops are inevitable. And the third hint is that because of the way the rules of this game are defined, each state has a unique pre-state. As in, this system is a deterministic system. You can define from any one state what state it's going to see next or what state it came from earlier. Right? So there is no ambiguity, and this also means that there is no branching. So from one state, it's not that it could lead to two new unique states. No, it's always going to be one unique state. So this over here is not possible. There's no branching or there's no merging either. So from two states, you would end up reaching one single state. This also is not possible because from each state, there is only one unique pre-state. So these two scenarios are not possible. Branching and merging can't happen. So having said all this, isn't it now just obvious that since the initial state was the state where all the bulbs were all on, so I'll just call that as the all on state. So yeah, so since we know that there are a finite number of states, we know that the system is eventually going to loop within itself. And since we know that each state has a unique pre-state, and we started with this was our initial state of all on states, thus all these points can only mean that the system is going to loop within a loop which already includes the all on state. So this all on state over here is going to be a part of the loop of which the system is going to loop within. I hope you guys understood this solution and thanks for watching.